So, in the past videos, we've been kind of exploring the Maxwell's equations in within like a field that has a source. So basically, like Maxwell's equations are these wave equations when they're inhomogeneous, as you can see here. And today's kind of an important video because we're going to be now looking at how we can apply these equations to a very important and useful scenario, which is that of like an antenna, right? So basically the idea is that the classic way of describing an antenna is as a infinitesimally, or not infinite, but as a small alternating current. So basically we have a tiny wire like this with an alternating current going back and forth. This is kind of like the standard way of describing an antenna. And so we're going to see how we can use our inhomogeneous equations to solve for the potentials and then the electric and the magnetic fields of a dipole antenna like this. So because this is a current, we're going to start with our second wave equation that involves the A potential field. So first let's describe our current, right? So J of X, Y, Z, T is equal to, we will use phasor notation, and we're also going to use the Dirac delta function that we talked about in the previous video. Bless me. So we can describe the charge here, or the current here, the current density by this parameter I delta L, and we'll say A e to the j omega t to describe the time variation, since this will just be like an alternating current, so it's just like a cosine function, and then delta in all directions, since we're kind of imagining this as like an infinitesimally small current source, and then this current source is in the z direction. Now, of course, as I mentioned, this is like a model, so like it's not actually infinitesimal, but it is a good model to work with to understand what's going on. And so similarly, we can then describe the potential function that'll result out of this, A of X, Y, Z, T, as the real part of some phasor A, which we will solve for, times e to the j omega t. Now, we're going to use this second wave equation that we have. And if we use our phasor A, we can then rewrite this as the Laplacian of A plus omega squared mu epsilon times our phasor A, is equal to our phasor J times mu. But since we're going to be looking at kind of similar to the last video, the simpler scenario, since we're looking outside of just directly that singularity at r greater than 0, we're just going to put 0 here, since there's no current source outside of that single wire, which is described by the Dirac delta function that we have. So now we have an equation that we can solve, and you'll notice it's very similar to the last video. So we're just going to apply the same the same derivation that we did last video to solve this equation. So in like the last video, we converted this to polar coordinates so that we could get an ordinary differential equation that looked like this. 1 over r squared d by dr of r squared dA over dr. And then we'll also note, one of the other things we can know is that since this current is only going in the up and down direction, we only have a magnetic field in the z direction, so that a sub x equals a sub y equals 0. And so we're only looking at the z component. So write down the rest of the equation. And so we can say that, and this looks very similar to the equation that we got from the last video, but we can just write this as mu times I delta. If we solve this, we'll get this differential equation. We get mu I delta over 4 pi r times e to the minus j beta r z. Bringing this to the if we look at this as a function of time as well, then we can see that we get this expression. Whoops. I change an L over 4 pi r times cosine of omega t minus beta r. And this resembles, so two things. One, this is a spherical wave. Clearly, we can prove that this is a spherical wave based on this expression because of this beta omega t minus beta r. And the other thing is that this looks very similar to the Biot-Savart law, right? Kind of in the last video, we drew a comparison to Coulomb's law. This looks very similar to the Biot-Savart law, which is pretty cool. So the next thing we want to do is we want to now use this potential to figure out what is H and what is E. So what we're going to do is we're going to convert what's currently in rectangular coordinates, we want to convert into spherical coordinates. So if you'll know that we can convert this coordinate by rewriting this as z is equal to cosine theta r minus sine theta in the theta direction. And so then to figure out what H is, we just have to take the curl of A. Now since we only have R component and theta component, we know that we will only get an omega component for H. And so the way you do curl in spherical coordinates is there's a expression for it. So the curl, or an identity for it, the curl of f in spherical coordinates is 1 over r squared sine theta and then the determinant of r times r theta and then r sine sine theta phi, or omega, sorry. And then partial r, partial theta, partial omega. And then the r component of f, r f theta, r sine theta f omega. Now this is just a notation, like this is just a formulation, like there's kind of just have to memorize it, but this is basically how you do curl in spherical coordinates, and we're going to use this a couple times in this video to figure out some stuff. But first, so h sub phi is just the curl of a for just the omega part, and to do that we just do 1 over r times partial over partial r of r a theta minus partial a sub r over partial theta. And then if you solve this, you will get, if you then plug everything in, you will get h of omega is equal to, j beta I delta L sine theta times 1 plus 1 over j beta r times e to the minus j beta r over 4 pi r. In the omega direction. And so this is a pretty important equation, so I'll go ahead and circle it, but this tells us what the magnetic field looks like for a dipole antenna. Now, from this, we can get the electric field by using, we will, next, to figure out the electric field, we're going to use one of the Maxwell's equations, which I am writing out here. Plus j, but since we're looking at the field where where there is no current source, where r is greater than 0, then we can ignore that and we're just left with this, and then we'll use the exact same determinant notation that I provided up here to be able to figure out what the curl of h is and then derive e from that. And I will not do it, but you should do it for yourself as a way of figuring out how to derive these equations. But you'll be left with two components, e of theta and e sub r. E theta is equal to j nabla beta I delta L sine theta one plus 1 over j beta r minus 1 over beta r whole squared e to the minus j beta r over 4 pi r. And then here, j times 2 nabla beta I times delta cosine theta of 1 over j beta r minus 1 over beta r whole squared e to the minus j beta r over 4 pi r. And so these are three really important equations. These are the equations that describe the electric and magnetic field for an antenna. And in the next video, we're going to look more into the properties of these. So I'll mention once again, like, take it upon yourselves to actually try deriving these by like solving using the curl formula I provided. Yeah, I would like take it upon yourselves to do that because it's just good practice that you'll probably learn from doing it. But yeah, in the next video we're gonna look more into the actual properties of these, which is very important. And yeah, thank you so much for watching. If you enjoyed the video, please like and subscribe, and feel free to ask any questions in the comments. But yeah, we'll be making another video where I'll explain more to the properties of these electric and magnetic fields of this antenna, talking about whether or not it's a wave, what they look like in the near region, whereas the far region, and how the power is affected, and looking at some interesting analogies that we can use to describe it. Thank you so much for watching once again.